Now, in this lecture, we are going to discuss about the geometric intuitions behind the gradient descent algorithm. Okay, so let's start. So now, in previous lecture, we have seen that to find a maximum and minimum value, we have to. So in previous lecture, what we seen? We have seen that to find our maximum and minimum, that we call x star is the maximum, that is our arc mean of our x. Let's call a functions as f of x. So this x star is our optimal value. So to find this optimal, we are using the derivative concept. For a scalar variable, we are using simple differentiation, that we denoted df by dx, and for vector we are using grad concept, that we will call grad of del of x is equals to 0. So to find this, we are using to find this maximum and minimum concept. Find the maxima and the minima, we are using this derivative concept. Now we are in previous lecture also we see that in all the cases, in some cases finding the derivative and solutions, and after finding the derivative, to find its solutions is not a easy task. Okay, because we are living in modern age of computer, so we have our huge capacity of computational power. So in this age we are using an iterative algorithm, that we call the gradient descent algorithm. Simple, this iterative algorithm. This is an iterative algorithm. Okay. So the simple concept is that in this algorithm, so first we have to maintain few steps. So in the first step, we have chosen a random number that we call x naught. So we had first guess randomly. First guess randomly of x star. X star means actually our final value, that we call our optimal value, and in first we have chosen this x naught randomly. Okay, this we choose the randomly, we are choosing this. Now in the next step we are just finding the x1 using the iterative, the first iterative one using the gradient descent algorithm. Simple, we are just using here ZD. In iterative one we are find the x1 value. In iteration 1. In second step, similarly we are using the gradient descent technique. We are finding the x2 value. Okay, so at the just we are continuing this process, but when we are fulfill our requirement, till now when we are fulfill our requirement, so after k iterations we find the value of xk, that is our iteration k. Okay, and according to our choices we are deciding, according to our situations, according to our choice, we are deciding this after k iteration, this value is optimal value or not. Okay, so this is the simple technique of our iteration technique. Okay, now come to the geometric intuitions behind the gradient descent technique. So first let's draw a picture. Let's draw a picture first. Okay, This is our independent axis. So and this is our dependent. Let's call a functions of f of x. Now let's draw a functions like this. Let's draw. Let's take this function is f of x. Okay. Now just you see this picture, then you can easily find that the optimal value is what? Here our optimal value, that is at x is equals to 0 in this function, that is at x is equals to 0 we have our optimal value, that is here we have simple minimum value at optimal value. But just you see, if you just draw it, you just draw in this side a slope, just draw a slope in this side. The slope is what? This side slope will be positive because the tan theta value here, theta value is lies between 0 to 90 degree. So if it is lies between 0 to 90 degree, so this side value will be positive. What will be the value of this side? If we just plot the slope of minimum point, then what will be the value of the slope value of this side? The slope value in this slide is equals to 0, 0, 0. And if we just plot the slope in that side, what will be the value of the slope in that side? So in that side value will be negative because here theta's value is what? Here theta value is greater than 90 degree but less than 180 degree. So in this slide the slope will be negative. In this side the slope will be negative. Okay. So just if we just see this geometric we have here, coming to one single decision. So decision is what? So just you see, just the both side of our minimum point we have changed our the slope, the sign of the slope is opposite. That is here actually here in this point is our minimum point, this point is our minimum point, and one side of our minimum point the slope is positive, one side is positive and another side the slope is negative. Okay. So simply if we just write this concept, in minimum one side in one side our slope is positive, in another slide our slope is negative. So this concept is simply used in gradient descent technique. Okay, let's come one by one. So before going to the gradient descent technique, let's remember this thing. So actually we have to find our optimal x star, that we call x star, optimal x that we call x star is what? That is our arc mean of x. Let's take a function f of x. And we also learned this theorem in logistic regression. Just remember the logistic regression. So minimum of f of x is what? Minus of, that is implies simply maximum of minimum of f of x, means just minus of f of x. Okay. And similarly here maximum of f of x means what? Implies that minimum of minus of x. Both the things are same, just we are using this concept situation wise. What is our situations, what is our problem, that's depend how equations we are choosing. Now let's come on concept. Just redraw the picture again. And let our graph is this is our graph. Let randomly we are choosing our point is here. Let randomly choosing our point is here. That is our x. Okay, when I choose this point randomly x naught, so at x naught what will be the our slope at this point? What will be the slope? This one. And we have seen that this side slope is also positive. Let's take this slope is our s1. Okay, now just to move another point, let's this point is our x1. Let's in this side our slope is what? This one, that we call s2. Let's take one point x3 here in this side. So in this side slope will be what? This one. So all the slope in this side is positive, but the one thing is that when you move closer to the minimum, actually here is our minimum point is here. Here is our minimum point. As we move closer to our minimum point, then what? Then the angle, the slope, the angle of the slope of our x-axis will decrease. Just see it. Here our angle is what? Here angle is theta. Let's theta 1. Here is angle is what? Here angle is our theta 2. Let's here angle is what? Here angle is our theta 3. So you just see this. As we move closer to our minimum point, our angle is reduced. Angle is reduced mean what? Our slope value is reduced. So as we move closer to, that is x star simple, that is our optimal value x star simple what? Our slope reduces. Okay, our slope reduces. As we move closer to our optimal point, the slope is reduced. Now, using these two concepts, these simple two concepts, we are coming to the gradient descent technique. Let's come gradient descent. Okay, so first let's, as if step by step, let's. So what is first? We have to pick a random point. First we have to pick a initial point. Let's call it is an x naught randomly. Okay, we will pick this point randomly. So let's draw a picture of it. I think then it will be clear. Here is our x star. So first we have chosen this point x naught initially here. Let here. So here in these directions our slope value will be positive. Okay. Now in next step what I have to do? In next step, in second step, we have to compute the point. that will be the closer to this minimum optimal point. So we have to pick a point such a way this point lie between x star and x naught. So let's take this point lie in here. So what will be the slope here? In this point slope will be this one. So how to pick this point? So simply using this formula, x1 is equals to at point x naught. Okay, now let's this r, here we are using one parameter, this called r. So what is the r here? This r is called the step size. How we move closer, how in what step we will move closer to our optimal point, that is x naught. So just see in this picture, if we choose the larger r value, then we cross the optimal value. This is not a good. And if we choose a small r step value, that is r value, then we will move the our optimal point slowly, and that will take is a large time taking matter. This is also not a good. So choosing the proper that is step size, this is a interesting topics of research. So I'm not coming to these topics, and in one lecture I promise you, in one lecture I will also discuss how to choose a proper r. So let's patient with me. Now in this lecture I am not discuss. So this value is called the step size. Okay, so this step size, let this step size value is 1 is equals to 1. Let's for some time let's take r is equals to 1, and r value be always positive. Okay, just remember this r value is always be positive. Now by using this technique I am going to show you that x1 lies between x0 and x0. But how? So if we just consider this formula, then x1 will be what? x1 is equals to x0 minus r, that is our 1, simply that is our 1, into this value is what? This value is simply the see this value is positive value. This value is positive value. Now I am going to subtract x0 by some positive value. So this implies what? This implies that our x1 value will be less than x0 value. Okay. Now I'm going to subtract some positive number to x0. So our x0 x1 value will be less than x0 value. So if this is less than if x1 is less than x0, then what? Then x1 will be closer to our x star value. So simply this means that x1 is closer to x star than x0. Okay. Now we are just see in this direction, in this side, that is called positive side. That is called positive side. We see these situations in positive side. Now let's see these situations in negative side. What will behave? Let's see. Let's draw. Again, let's draw same picture. Let's draw the same picture. Okay. Let's take a point in negative side. Let's take our point is here. Let's take our point is x naught. Initially we are taking the negative point. So what will be the slope here in this side? Slope in this side will be there here. So what is it? This one is in this side. Slope is the angle. Here angle is what? Here angle is greater than 90 degree and less than 180 degree. So in this side our slope is negative. Okay, in this side slope will be. And now we are interested choose a point. Here is our optimal point x star, and now we are interested to choose a point such that this point lies between x star and x naught, and this point is also greater than from x naught. Let's our point will be here x1. Now how will choose it? Just using the same formula. So let's see how it works, how this formula works. So actually what is our formula? X1 is equals to x0 minus r into df by dx of our initial point x0. Now what will be this equation? X0 minus r, simple, we are assume that our is 1, and this, what is the in negative side, what is this value? This value is negative. So simply what is the equation? Is equals to positive, means positive here. So now here we are adding some value to our x1. So if we add some value to our x0, then x1 will be what? X. This implies that our x1 is greater than x0. Simple, in these situations, both the situations, it will works. This equation is to work. Now here in this situation we are moved closer to our optimal value. So just see, using this formula in positive side as well as in negative side, this it work, this is work. So I think the step 2 is clear, all of you. Now coming to our third step, step number 3. Let's come. This is our step number 2. Let's come to our step number 3. So in step number 3 we are repeating the same process. In how? In step number 3, simply we are calculating x2 using the same technique, that is x1 minus r of del f by del x at the same x1 point. Just we are simply repeating this technique. Okay, here. So just we are repeating this technique iteratively. How it is repeating? Just redraw this picture again. We are repeating in such a way that this is our graph and this is our optimal point. This is our initial point x0. This is our initial point, that is x0. Now we are choosing in first step x1 here, in second step x2 here, in third step x3 here. As time increases, as iteration increases, we are going to move closer and closer to our optimal point, that is x star. Okay, now iteration will be after ith iterations we are calculating xi plus 1 I minus r of df by dx at point xi. This is simple our iterative technique. This is called the gradient descent technique. Okay, now you just see one observations from this technique. Just see these observations. So just coming to this picture, as we are move closer to our optimal point, that is x star, our slope value is decreased. Okay, slope value is decreased here, that is since because s1 is here greater than s2 is greater than s3 is greater than dot 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 dot. As suppose let's take our, we have iterated k number, we are using the k number of iterations here. Okay, so simply if we just write down this concept, simply here we are moving first, we are just jumping up from x initial point to x1 to x0, we are just jumping this point a larger step. Then from x1 to x2 we are using the smaller step, a smaller step than previous. In x3 then smaller, then x3, x4, as we simply just we are x, suppose let's take xk plus 1. So we are jumping to this to this, from this here, from here, and from xk to here. So as we jumping, our jumping steps is decreased, because as we move closer and closer to our optimal point, our slope value is decreased. So let's, we in first step we are decreasing 0.3, then we are decreasing 0.1, next let's take we are decreasing 0.05, let's after keep we are decreasing 0.0001. So according to our choice, according to our requirement, we have using our iterations. Okay, so if our differences is so small, that is our differences means from what, xk plus 1 to xk is very small, as it is depend on our requirement, then we are terminated. Then we are terminated. Then we are terminated our iterations and declare that our optimal value is what, xk. Okay, that's depend on our situations, how accurate value we are needed. Okay, we in simple in the gradient descent technique, sometimes we are not get the exact value, but here as our requirement we can choose to closer and closer to our optimal value. Okay, this is simply a iterative technique. Now I think it is clear all of you. Now just revisit this lecture. So just we are using here the gradient descent technique as programmatically or iterative technique. First we have what we have to do. First we have to choose a random point. Okay, we have choose a random point, and using this random point we are using the iteration. In first iterations we choose one point, we are calculated one point that is closer from the initial point to our optimal point. So just we are increasing the iterations. So how to choose this point that is called that is closer to our optimal point? Simple, here we are using this formula, that is xi, that is what, that is our xi plus 1 is equals to ixi minus r into df by dx into xi. Just here we are using this formula to iterate it. Just we are just moving the point I as our requirement. If you see that our xk plus, after k iteration we are see, if we see that xk plus 1 value differences of the xk plus 1 of and xk is very small, then we are terminated our iterations and we are deciding that our xk is our optimal value according to our requirement. Okay, I think this is simple, and I think you have no any problem about gradient descents. If you have any problem, please comment below.